So we were on this part C, isn't it? We were calculating the particular part C. Part A and part B is done. We wanted to know the magnetic field for these wires. Part B again. Okay, so okay, let us see in part B what is happening, that you have, okay, this is the set of magnetic field, mean set of wires, isn't it? And let me raise it fully. This is my wire, and they want the magnetic field somewhere over here. Okay, somewhere over here, which is point B. Now you look over here. I can create. See how to find this. This is also a semi-infinite wire only. But here the problem is we'll follow this principle. Like as we know, that if the wire is shifted, then upward angle becomes beta. And if this is A, this is A, because the coordinate of B is A minus A comma 0, isn't it? So this angle is 45, means beta is 45 while alpha is 90. Are you able to get me? Because this angle will go till infinity. Are you able to get me? Is it clear? Yeah. Now for this wire, which is going till infinity, once again you have the same coordinates and all. The point is this is also A, and this angle is also 45, but it is this time it is not going to be considered as negative, while another angle alpha is 90. So B at B is due to the, let's suppose this is first wire and this is second wire, so it is B due to first wire plus B due to second wire. B due to first wire, mu naught I by, so if this length is A, the perpendicular length is still A, so 4 pi A sine alpha means sine 90 minus sine beta, because it is upward direction. And L cross R, what is L cap? If you look over here, the current was going like this way, so L cap is minus I cap and R is minus J cap. Are you able to get me or not? This is B1 plus B2 is once again same, mu naught I by, distance is still same, 4 pi A, but here it is downward, so sine 90 plus sine 45. And L cap is I J cap and R cap is I cap. So you multiply, you'll get the answer. Is it clear? So this is your task. This is you are going to do. Okay. The last point was to find the magnetic field at point C. Now for that, I'll discuss it once again. I want to find the magnetic field at point C. What I should do? Look over here. If this is X axis, this is Y axis, and this is Z axis. And the wires are lying in X axis like this way. And you want to find the magnetic field at point C. And these wires are infinite along these axes. This is point C. Now, basically for this, I can see that if you look into over here, then this point C is nothing but a distance perpendicular to the semi-infinite wire, where where beta is equal to how much? 0, while alpha is equal to 90. Here also it is same. Yeah, beta is 0, while alpha is equal to 90. So I can write the magnetic field at point C that it is mu naught I. Distance is still same. Distance of both of them is this gap, which is A. So mu naught I by 4 pi A. For first wire, sine alpha 90 plus sine 0. I'm not considering that. Got it? Yeah. But for first wire, let's say this is my first wire and this is second wire. L cap is J cap, isn't it? While R cap is Z cap, isn't it? K cap. Yes. Second, same mu naught I by 4 pi I. This one, once again, L cap is minus I cap cross. Then what it is? Once again, R cap is Z K cap. Are you able to get me or not? Is it clear? So the solve this, you'll get the answer. So this is mu naught I by 4 pi A common. J cross K is what? J cross K is I, and I cross K is minus J, minus minus plus. So plus J. This is your magnetic field at point C. So I'm telling you one thing, always follow this principle, what I'm saying to you. Consider alpha and beta and then write L cap cross R cap, which will give you a clear idea. Okay. Is this clear? Can I move ahead? Okay. Let's do one more example. It is saying that okay, this kind of a configuration is there. The current is going like this way. Okay. And this angle is alpha. This angle is also how much? Alpha. This is point 0 comma 0. This is point A comma 0, and this is point B minus A comma 0. If these wires are infinite wires, then find the magnetic field at A and B. Okay, so tell me what will be the answer. You do not have to find alpha. You have to find magnetic field at point A and point B. Just think it is easy. See, first of all, whatever is going to happen, you have to first remember that you need to construct a perpendicular distance, isn't it? Yes, isn't it or not? Not it. Now, if this is A, this is alpha, then this is what? I can write now. A sine alpha. This is all A sine alpha, isn't it? Then one angle will be 90, another angle will be, this will be 90 minus alpha. Got it? So, magnetic field at A, let's suppose this is first wire, this is second wire. So, it is what? Magnetic field due to first wire vector plus magnetic field due to second wire vector. So, it is mu naught I by 4 pi A. A is my A sine alpha. Then, sine 90 plus sine 90 minus alpha. Got it? Uh-huh. And then L cap. Now let us okay. So if I write L cap plus R cap. Okay. So if you want to write L cap plus R cap, what it will become? See, this L cap and R cap are almost in perpendicular directions or not. So for this, if I put my means whatever happens, the magnetic field will be kind of perpendicular to the plane of L cap and R cap, isn't it? Because this is a cross product. So if it is X and Y plane, then it will be always along Z axis. Are you able to get me or not? For this also, if it is X and Y plane, then the magnetic field will be in the Z axis plane. So I'm writing directly K cap. Are you able to get me? And then multiplying this by 2 because both of them are at same distance and same angles are there. Okay. So answer is mu naught I by 2 pi A sine alpha, and here it is 1 plus cos alpha k cap, that is mu naught I by 2 pi A sine alpha. 1 plus cos alpha is what? 2 cos 2 cos square alpha by 2. Yes, so 2 got cancelled, and this is mu naught I by pi A sine alpha can be written as 2 sine alpha by 2 cos alpha by 2, and this is cos square alpha by 2. So this got cancelled. So this is mu naught I by twice pi A cot alpha by 2. Is it clear? Similarly, can you find the magnetic field at point B? Do it. How to imagine it? See, for this one, this can be a perpendicular point or not, isn't it? Can we construct with the help of B over here? Let me do one thing. Let me erase this. We'll bring it over here. This is my perpendicular length. Yes. Now this length is A. Yes. From here to here, this particular length is A or not? This is 90. This is alpha. Then this angle is 90 minus alpha or not? And then this is alpha. Correct? So if this is alpha, this is A, then can I use this length that is perpendicular distance? Yes or no? But how to find the magnetic field over there? For this wire, to become a tedious task. Hmm, how to find the magnetic field at B? It's B it is asking now. Okay, we'll have to consider that same approach. I think for this it is perpendicular, then this it is perpendicular. The perpendicular distances. Yeah, so because, okay, so we will just consider the perpendicular distances, go ahead or not? Because magnetic field is only calculated for the perpendicular distance. Okay, so let it be alpha. So then, if this is A, this is how much? Sine alpha is equal to perpendicular by hypotenuse. So hypotenuse is equal to A by sine alpha. Right or not? So then B at B is due to B due to 1 plus B due to 2. So due to 1, it will be mu naught I by 4 pi A by sine alpha. So sine alpha goes in numerator, isn't it? Then one angle will be 0, another angle will be 90 or not. So sine 0 plus sine 90. L cap, and once again if you consider this is L cap and R cap. Okay. So L cap is this side, R cap is towards this side, isn't it? So I'm considering this as X and Y. So the magnetic field L cap is I cap cross J cap, isn't it? So then it is K cap, isn't it? Similarly, if I just consider the B over here, means if I want to find the perpendicular distance will be this, isn't it? And once again, if you find the magnetic field L cap cross R cap, it is along K cap only, isn't it? So the answer is just multiply this by 2. Answer is mu naught I sine alpha by 2 pi A. That's your answer. K cap. Clear? This is also K cap. Okay? Clear or not? Okay? Okay. Uh, 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 uh. Okay. Okay, so let us move on to our next topic. Okay. give the heading. So first we did find the magnetic field due to the straight wire, isn't it? Now we'll find the magnetic field due to a current carrying circular coil. Magnetic field due to a current carrying circular. Are you able to get me? So this time I have a circular coil, a perfect circular coil. Okay, 1 minute. And due to that, we want to find the magnetic field. Got it or not? Is there any kind of background noise? No, no. Okay. So look over here. Now, the first task is I want to find the magnetic field at the center of the circular coil. Okay, now, yes. So look over here. This circular coil is of n turns, and some current I is flowing in this circular coil. Okay, and I want to find the magnetic field at the center O. Got it? Let's suppose the radius of the circular coil is R. Got it? So I want to find what is the magnetic field at the center. So how to do it? Can you tell me? Mm-hmm. Think means how to derive it or how to make it easy. So should I give you the direct formula or should I make you understand what I should do? Tell me. Derivation. No, ring will come. Circular coil, I think it will not come. Alright, let us see. What is the formula of Barrett-Savitt's law? Mu naught I by 4 pi I dl cross r by r square, isn't it? Yes. In simple terms, in non-vector form, it is mu naught I is equal to mu naught. Why I am writing I two times? Mu naught I by 4 pi I dl sine theta, isn't it? This is the form, isn't it? Correct now? Now look over here. So why there is a problem over here? See, I know my magnetic field. This is mu naught I dl sine theta by 4 pi r. This magnetic field I. This is mu naught I by 4 pi 1 by r square dl cross r. Now, if you look at small component, any small component dl, for that, the direction is actually along the tangents or not. So IDL has a direction along the, and it is always at a distance r from the center of the circle. Correct. 1 minute, let me close the door. Okay. So it is IDL has always the direction along the tangents. Are you able to get me or not? So you got one nice thing that, sir, whatever happens, angle between ideal and distance r is always 90 degrees. How much is that always? Yes. So this dv simplifies. This is just mu naught I dl by 4 pi radius r, isn't it? Yeah. So now if I integrate dv, mu naught I by 4 pi r is outside integral dl. But what is integral dl? Mu naught I by 4 pi r. Length, if I integrate length, it will become 2 pi r or not. So 2 pi cancel, r cancel. So it is what? Mu naught I by 2. Is I'm doing any mistake or what? Let me check Bart's law. I think it will be r square always. Oh, it is. Sorry. Yeah, it is r square always. This was r cube. That's why I'm thinking, where is my another r? This is r cube. Here, here it is r square. So mu naught I by 2r. That's my formula of magnetic field at the center. Are you able to get me or not? Is it clear? So look over here. If there are n turns, then magnetic field at the center is given by formula mu naught Ni by 2r. Are you able to get me? Yeah, in the derivation here n is 1. Are you able to get me? Write it fast, then I'll move ahead. Okay. Now the question arises that, sir, as there are n loops, you can find the answer. Here n can also be integer. It can also be a fraction. Go ahead or not, like half loop, quarter loop, or something like that. Okay. But the question arises that, sir, if you have given this answer, then if I am including current and all, then what about the R? Let's suppose if I have a R, okay, in between these 2 points there is a arc over here. Go ahead or not. And for that, if I want to find the magnetic field, means in this arc there is some kind of a current which is flowing. Okay. What is happening? Now it is perfect. So now some kind of a current is flowing in this I, and the radius is given R, which makes some angle theta at the center. And you want to find the magnetic field at this center. So magnetic field, yeah, magnetic field at the center is given by, the formula for this is, it is given by formula B is equal to, no, set 1 minute. Mhm. It is given by formula B is equal to mu naught Ni by mu naught Ni. No, no, let us not write the number of loops in that. So it is mu naught, yeah, mu naught I by 2r theta by 2 pi. Okay, this is the formula. Is that clear? Yeah, where theta is the angle subtended by the r at the center. Is this clear? Today is which day is District 26th, huh? Yeah. So today evening we will have a capacitance class, okay? Okay. Yeah. Now the question arises that, sir, where will be the direction of magnetic field? As magnetic field is a vector quantity, then what you will do? There is a process. The process is you will curl your right hand fingers. Yeah. In the direction of current. You will curl your right hand fingers in the direction of current. Then the thumb, yeah, gives the direction of, yeah, gives the direction of magnetic field on the axis of coil. It will not be anywhere else. It will be on directly always on the axis of the coil. Are you able to get me or not? Is it clear? Mhm. Is it clear or not? Confirm? Okay. Now, so this was for the case of our circular coil, and then now basically the circular coil and we were finding at the center. But what happens if we consider the circular coil? Okay, like this way, and I want to find the magnetic field at the axis of the center of circular coil. Got it? Yeah. And I want to find the magnetic field at this point somewhere over here. Let's suppose it's, yeah. So let's suppose some kind of a current I is flowing in that, and this point is at some distance x away from here, and the radius of the coil is, many people write it z. I'll write it z because it is easier to remember in terms of electric field and all. Okay, then if the radius of the circular coil is given as r, okay, then find the magnetic field at point P. Think. So this is magnetic field on the axis of circular coil. I think I have a better diagram for it. Right. No, nothing is working on this. Okay, so I want to find, see, this is my circular coil. A current is rotating. Okay, here and this is my, they are saying the same thing, that sir, this is my z axis from here to here. Got it. And radius they have kept as a instead of, okay, so let us we have been also following a in a straight line, so let us keep it as a. Okay, and I want to find the magnetic field if a current is rotating in this like this way. So basically ideal is like this way, isn't it? So the idea is very simple, that first we'll find due to a very small element, let us call it as IDL. Now this IDL will be located at some distance away from point P, isn't it? So look over here, this is my IDL which is I'm considering, and this is located at some angle from point P. I call it as, let's say this angle is theta. Got it? So this is called as radius R, and this radius R as a value. R is equal to nothing but root under Z square plus A square. Are you able to get me? Now, point over here is, the biggest problem over here is that when I'm finding the magnetic field, so due to this current, I'm finding the magnetic field now. But due to this element, if I am looking for the magnetic field, this particular element, so see this, see if I am although considering everything in XY plane and all, if you look over here as R, what is this R vector? This R vector is along, I can say that it is Z. If you look over here, it is Z uh, K cap plus A I cap or not? Tell me yes or no. Not even A I cap. A is along the formation. We do not know where it is. So let's suppose if I'm considering like that, that Z is, yeah, I'm writing R vector as AI cap. Still, I'm just considering X AI cap plus ZK cap. So mod, yeah. So if I write R cap, it is AI cap plus ZK cap divided by root over A square plus Z square, isn't it? And if you look into the Bayes-Servit's law, it is what? If you, it is IDL cross R cap, isn't it? But this DL is changing all the time, isn't it? Correct. So if it is IDL, if I am considering ideal over here, then how to write it, that's a big problem or not? Yes, are you able to get me? So what we imagine that, sir, yes, better you if you go to the conversion in form of vector form, it's a very hard thing. But we know that for this current, the magnetic field will be a perpendicular, isn't it? Yes. So this ideal, if ideal is like this way, so then the magnetic field will be this way or not? Yes, perpendicular to the line joining ideal and DL. Are you able to get me? So ideal will have a tangent like this way, and this is perpendicular to the plane of all of them. Are you able to get me or not? So this is what is happening. This is ideal, this is R. The magnetic field, DH means magnetic field. Remember, DH is showing what? dB. Consider it to be dB. So magnetic field is perpendicular or not? Tell me. Yes, is this clear? So look over here. This magnetic field will create some theta with the plane of x-axis. Let's suppose this is some x-axis. So this angle is going to be theta. Okay. And this is, if this is dB, then I have two components, dB cos theta and then dB sin theta. Is it clear? Sorry. This is not cos theta. See, this is theta. This is whole is perpendicular. So if this is 90 minus theta, this is theta. This is theta. Yeah, this will be theta with the z axis. With the z axis only, no? See, yeah. So this is point P. So this is dV sine theta. This is dB, and this is dB cos theta. Clear? Clear or not? So look over here. When you will observe, see, if I consider an ideal just identically opposite of it, for this also there will be two components or not? Hello, can you hear me? Once again. Okay, 1 minute. 1 minute. Okay, now it is audible. So point is very simple. When I just considered DL over here, there is an identically opposite DL in the opposite direction or not? Now for that also I'll get some magnetic field perpendicular to its DL component. And once again, if this angle is theta, this angle is also how much? Theta. So what do you observe? That the perpendicular components, mean the sine theta components, will cancel each other while the cos theta components will only exist. Yeah. So only what thing exists? Yeah. Yeah. So okay. So look over here. So therefore, if I write dB, so it will be integral. Means if I write net magnetic field, yeah. So it will be integral dB dV cos theta. Are you able to get me? So B net will be equal to what? Basically, what is our dB over here? It is nothing but mu naught I dl. And if you look over IDL and R, then R is also perpendicular to this DL or not? Look over here. Sine 90, yeah. divided by 4 pi r square, which is z square plus a square cos theta. Is that clear? So what I'll get as b net, it is mu naught I by 4 pi z square plus a square will be, can I take z square plus a square outside? Because z is fixed, a is also fixed, isn't it? Z square plus a square outside. Even cos theta is fixed. Theta is also fixed, isn't it? Yeah, because it is a ring element. So every time I'll get the same theta. Integral dl. Are you able to get me or not? So what is integral dl? B net is equal to mu naught I cos theta z square 4 pi z square plus a square. What is integral dl? Tell me. Integral dl will be the 2 pi a or not? Pi a. Are you able to get me? So this 2 pi got cancelled and I'll get 2. So mu naught I a by 2 z square plus r square. Sorry, z square plus a square. What is cos theta? Perpendicular. Sorry, cos theta is base by hypotenuse. A by. Yes. So B net, you got the formula of net magnetic field at the axis of circular coil. Yeah, so it is mu naught I a square by twice z square plus a square to the power of 3 by 2. Is this clear? And that is along which direction? Along, look over here. This is z. This is z axis on. So look over here. Is it parallel to the x axis or not? So along x axis. Are you able to get me? Is that clear? Okay, write it fast. Hello?